In this video, I would like to um, basically document my journey towards preparing, um, basically my preparation for my next quiz for differential calculus 1. So these are all of the formulas that have to be memorized. Well, not all. I haven't studied log and exponential functions, finding the derivatives of those kinds of functions. But right now, I'll just give a rundown on the formulas that we have so far. So we start first with the trig functions. So sine, cosine, tangent, secant, cotangent, and cosecant. So each one has a derivative. Derivative of sine, let's say usually it's x, right? But we'll use u this time. So the derivative of sine u is cosine u times d over dx. Basically, this one is the derivative. This means the d over dx means the derivative of u. So you have to multiply it with uh, the derivative of sine u, which is cosine u itself. So yeah, cosine u, derivative of it is negative sine u times du over dx. Tangent u, the derivative of it is secant squared u times d over dx. Secant u, its derivative is equal to secant u times tangent u times du over dx. And then cotangent u is negative cosecant raised to 2 u times du over dx. Cosecant u is equal to negative cosecant times cotangent u du over dx. So the way I memorize it, well, let's start here again. So sine u, cosine u. Just think that, well, they're derivatives of each other. But you cannot say for the other way around because the derivative of cosine u is sine u but with a negative sign. So you have to take note of that specifically. So from sine u, you have cosine u. From cosine u, you have negative sine u. Okay, for tangent u, so you just have to know that coming from tangent u, you end up becoming secant u, but then there's a raise to 2. So take note of that. If it's the other way around, you're looking for the derivative of secant u. It's going to be itself, secant u, times tangent u. So if you remember this formula, it's easier to memorize this because you can see that they're related. So if you have tangent, it's going to be secant raised to 2. If you have secant, it's going to be secant itself times the tangent. For cotangent, so that's basically because tangent and cotangent are cofunctions to each other. So you can say that if, for example, you have tangent, your derivative of it is going to be with a raised to 2. Same goes with cotangent. So derivative of cotangent is something with a raised to 2. So at least that's the way I remember it. So the derivative of cotangent u is equal to negative cosecant squared u times d over dx. So cotangent and then cosecant. This time, though, although there is a common detail for the derivatives of the two cofunctions, for cotangent, its derivative is negative. So not just cosecant, it's negative. And the same thing goes if you're looking for the derivative of cosecant itself. It's going to be negative 2. And you just copy it, just like the way you copy the first part of secant u's derivative, which is just itself, times tan u in this case. In this case, for cosecant, again, after copying itself, you just write cotangent u. So CSCU, cotangent u, or cotangent u, CSCU, doesn't matter. Either way, it's correct because, again, in multiplication, it doesn't really matter. 1 times 2 is equal to 2 times 1 is equal to 2. So the order don't matter, basically. So inverse trig functions. So the derivative of negative sine sorry, not negative sign. The derivative of this, by the way, the one that says raised to negative 1, that means arc. So the derivative of arc sine of u is equal to the derivative of u in the numerator divided by, under the radical sign, we'll have 1 minus u squared. So I'll keep it fast. For cosine, for the derivative of arc cosine, it's the same exact thing except you add a negative sign. Okay? So numerator is still u, I think it's called prime. Basically the derivative of u. And the denominator is exactly the same, square root of 1 minus u squared. And yeah, you just have a negative sign. How about tangent, derivative of arctangent? So the numerator is still the same, but it's going to be positive again this time, just like for arcsine. However, in the denominator, there's no more radical sign. It's going to be 1 plus u squared. So initially for arcsine and arccosine, the denominator is 1 minus u squared, right? For both, not just for arctangent, also for arccotangent, the next one, it's gonna be still 1 and u squared, but this time there's a plus sign and the radical sign is absent. And yes, chronologically, if you memorize it this way, so in descending order, you can notice that for arctangent, the numerator is positive, just like for arcsine. And for cotangent, the numerator is negative, just like arccosine. So that's one way that could help you memorize it more easily. For arcsecant, so the numerator is not going to be the derivative of u. It's just going to be u itself. Same thing goes for cosecant. So I believe one way to memorize is, well, secant and cosecant, I don't think they're cofunctions. But then, yeah, you just have to think that secant and cosecant will have this kind of orientation. It's exactly the same numerator and denominator, only difference is the sign. So for secant, it's going to be positive. Just like in the case of the derivatives of trig functions, secant was never negative. There was never any negative sign. This is all positive. Where did we get a negative sign? Somewhere where it involved cosecant. Same thing goes here. So if you see a negative sign, that's, well, if you see CSC raised to negative 1, or basically arc cosecant, you will have a minus sign. Okay? Okay. Definition of hyperbolic functions. I won't discuss this anymore. Sorry, what just happened? Chat, am I still here? Anyways, I think it's still working. Okay. Definition of hyperbolic functions. So let's first start with sine and cosine. So you might want to compare the list of formulas under hyperbolic functions with the derivatives of trig functions, because they're very similar, although there are very important differences that you have to know. So for example, so one of the similarities is that for here in this part, the derivative of sine hu is equal to cosine hu times du over dx. Let me just fix my writing. This is supposed to be u. It looked like a y. Anyways, going back. So sine hu is derivative of sine hu is equal to cosine hu. Imagine that the h letters were not there. It's exactly the same as the one here in the derivative of sine u, which is cosine u. Now, in the derivative of trig function, so more specifically the derivative of cosine u, it is equal to negative sine u. That is not the case for its counterpart in the definitions of hyperbolic functions, because the derivative of cosine hu is sine hu. There's no negative sign. So you have to take note of that. Confusion can cost a lot. Okay, tangent hu is equal to secant h raised to 2u. So similar, actually it's the same concept here. So the derivative of tan u is equal to secant squared u times du dx over dx. Same here. The only difference is you have an h. Okay? For secant, so the difference here, so in the list of inverse trig functions, looking here specifically, arcsecant has no negative sign, right? Just the same as its counterpart in the derivatives of trig functions. So both of them are positive. But in the case of hyperbolic functions, the derivative of secant hu is equal to a negative. But essentially, it's the same. So you just copy secant hu, and then you multiply it with tangent hu. So that's the thing. You have to know, basically, that for the first three hyperbolic functions, sine, cosine, tangent, they're all positive. For secant, cotangent, cosecant, they're all negative. So, yeah. Unlike in the derivatives of trig functions, what's only negative are this one, this, and this. But more notably, these two. Okay? So, the derivative of cotangent hu is equal to the negative, is equal to negative cosecant h squared u. Where do we see that? It's legit the same. So, cotangent u is negative cosecant squared u here. So, same concept. Same pattern, so don't worry. The derivative of cosecant hu is, well, it's also the same. So, negative cosecant u cotangent u times d over dx. Okay, let's highlight the similarities. They're all, both of these guys are, both of these pairs are very similar. So are these. What else is similar? This one too. Right? What else? Okay, that's it. So if you memorize in a way where you lay it out exactly like this, you can see that this is negative, this one's positive, but this one's positive, this one's negative. Again, that's just my strategy. So I'd like to memorize it by writing the list in this exact order. Okay? Yeah, I'll talk about a few identities. I believe these are called identities. So Pythagorean identities, these can help if ever you could convert two or just one term into one or two parts. Well, that's going to be useful for simplification. So granted the scenario where you have cosine squared x and sine squared x, and there's a plus sign in the middle, that's one. You can turn those two terms into one. Same goes for if you see 1 plus tangent squared x, that's equal to secant raised to 2x. Same thing for 1 plus cotangent squared x, they're both equal to cosecant squared x. The reason why I have this red annotation, when I was writing these formulas, more specifically these two, I initially placed a minus sign. So that's wrong. So if you don't want to follow my initial mistake, always remember, for Pythagorean identities, there are no minus signs. And one thing to remember, because this one's easy, actually. For these two, what you have to remember is tangent and cotangent, they are cofunctions, right? But they will never be bigger in a specific sense compared to, for example, for tangent, it's not bigger than secant squared x. Same thing for cotangent squared x. It's not bigger than cosecant squared x. As you can see, logically, cotangent squared x plus 1 is only equal to cosecant squared x. So if there's no plus 1, this one's smaller. Same logic goes for this. That's just one way that I recommend that you memorize. For double angle formulas, so the first one's easy. Sine 2x is equal to 2 sine x cosine x. Or in other words, 2 cosine x sine x. Again, multiplication order doesn't matter in the scenario depicted. Cosine 2x is equal to 2 cosine squared x minus 1 is equal to 1 minus 2 sine x, 2 sine squared x. You have to memorize it specifically in this order, okay? It is wrong to say that cosine 2x is equal to 2 sine squared x minus 1. That's wrong. There's a reason why cosine squared x is the one written first before the minus 1. And yeah, don't forget the 2. Again, what's written as red is what I forgot to put. Okay? So, yeah. From this idea, you can say, I think it's safe to say that cosine squared x is bigger than sine squared x. So it's written that way. And it makes sense because this is, if you cannot memorize these two, at least memorize this. So if cosine squared x plus sine squared x is equal to 1, what if there is a minus sign in the middle instead of a plus? Well, that's equal to this. Okay? And for tangent to x, that's going to be 2 tan x over 1 minus tan squared. Sorry, this is supposed to be x. For uniformity. Because initially, I translated all these coming from x being theta. Theta. Okay? Sum and difference formulas. Sine x plus minus y. This is going to be sine x cos y plus minus cos x sine y. So just think that for sine x plus minus y, sine cosine cosine sine. For cosine x plus minus y, it's going to be cosine cosine sine sine. But nevertheless, it's still xy, 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 xy. And what's in the middle is essentially the plus minus sign. Okay? For tangent x plus minus y, so that's going to be tan x plus minus tan y in the numerator. And in the denominator, it's going to be 1 plus minus tan x tan y. So, yeah, this is written in red. I don't remember it. So, I still have to recall it. By the way, I almost forgot to mention this too. Actually, I don't like tan 2x. I still don't remember. Let's see if there's a pattern. Never mind. So tan 2x is 2 tan x over 1 minus tan squared x. That's it. Find a way to memorize it on your own. For half angle formulas, so sine x over 2. If it's sine, then it's going to be 1 plus cosine x over 2. For sine and cosine, it's always going to be over 2. For sine, it's going to be 1 plus cosine x in the numerator. All of the half angle formulas have a radical sign and the plus minus sign from outside. So that's the first step to memorize. What I previously said is going to be the distinction among the three. So again, for sine x over 2, that's going to be 1 plus cos x over 2. For cos x over 2, that's going to be a minus this time. Same thing in the numerator, but this time a minus. For tan x over 2, it's essentially the numerator here over the numerator here. So 1 plus cos x over 1 minus cos x. So that's it. Next video will be on log functions and exponential functions. But expect in the next videos, I'll be recording video montages of me answering several questions that where these formulas are used. So yeah, that's it. Thanks for watching.